Tonight we're going to do something a little unusual. I'm going to fabricate optical elements from food. Specifically, what I'm going to do is make diffraction gratings on sugar candy and chocolate. If you want to break up white light into its component spectrum, you can do that either with refraction through a prism or through diffraction with a diffraction grating. With a prism, the light is broken up simply because when white light enters a higher index medium like glass from air, the light slows, and if it enters at an angle, the light will bend or be refracted. But that bending property is different for different wavelengths. It's a property called dispersion. And so when a prism interacts with a light beam, it will refract the beam maybe 50 or 60 degrees. But it will refract the red light and the blue light differently. And so it will take that beam, move it a great deal onto a screen, a great angle of incidence, a great change in angle. But the change will be slightly different between the colors, and so you'll see a rainbow. When you use a diffraction grating, you're relying on the property of diffraction. And what that is the interaction of the electric field of the light and the electric field of the surface. Means that when you're very near an abrupt change in the surface profile, the light will be drawn or essentially pulled apart. It will spread the light. And when you have a very large surface, like say a large mirror like this one, or you move through a large aperture like a doorway or a big window, the reflective surface overwhelms the effect of the diffraction that occurs at the edges, because the diffraction only occurs within about a wavelength distance from the edge. And so when you look at a large mirror, you'll see the diffraction pattern in there. It's in there. And you'll see a rainbow caused by the diffraction. But you can't possibly dig that out of all of the light that's being reflected and not diffracted from the surface. However, if you narrow the mirror substantially down to the order of a wavelength of light, the diffracted light begins to become the dominant light. And so you'll see a spectrum formed by the effect of the diffraction. Diffraction gratings can be produced by producing very fine mirrors or very fine reflections in a variety of materials. This aluminum plate I have is a machined plate. Its tooling marks from the machining process cause the light from the room to actually be diffracted or bent or moved laterally into small rainbow bands. And you'll see the same process in a CD, and you can see the same process occur in, say, a glassy material. Glass is often used for the optical elements in, say, spectrographs because of its very precise manufacture. You can also see the effect of diffraction in other materials like, say, plastic. You can purchase plastic films that have a profile placed on them that create a huge number of parallel reflective surfaces, or mirrors basically, in a large piece of material like this, which you can get on eBay for maybe $10 a square foot. And the film has a profile on one surface and a flat surface on the other. And we can use this plastic to impart or to mold other materials like chocolate and like sugar candy. When we do so, what effectively we're doing is relying on the effect of the spread of that light by the diffractive effect to create a rainbow. And the way that that works is that when the small strip, the tiny little mirror, diffracts the light and spreads it out over a large angle, what happens is that the light of a particular color, let's say blue light, will take a certain number of wavelengths to move from the mirror or the reflector to a screen or some surface on which it's going to be projected. At a straight shot from the mirror to the screen, there's a certain number of waves. But as you move laterally, the triangles, the hypotenuses of the triangles, begin to increase. And when that hypotenuse is one wavelength greater than the straight line shot, the waves of light will interfere with each other constructively, and you'll see a bright band. Because the aperture, the wavelength, the size of the reflector is on the order of the wavelength of light, the light that's coming off of it is coherent, and that's why that happens. because the distance that is required to get constructive interference is one wavelength. If you have a longer wavelength of light, like red, it takes a longer distance. It has to move out farther laterally before you get one full wavelength of light for the constructive interference. As a result, when you look at the output of a diffraction grating, you will get bands on each side of the center or the perpendicular from the mirror. And those bands will be repeated each time you have a constructive interference of one wave. And those bands, which are called orders, will not be representative of the destruction of light or the production of energy from nothing. What they are is they're just a grouping of the light, a clumping of the energy into these individual bands. And so based on quantum mechanical effects, a diffraction grating is a method of separating light that does not require refraction, meaning moving through a surface, and it can be done by profiling a material that has some reflectivity, as long as that profile is formed at the dimension of light, in other words, a 50,000th of an inch or maybe a 2,000th of a millimeter, you will get a diffraction effect. You'll see a rainbow. In order to do that in materials other than glass or plastic or metal, something like food, you have to very carefully handle the materials so that they will reproduce that surface profile. So tonight what we're going to do is we're going to use a plastic mold, or this plastic material, to essentially impart on the surface of the sugar candy and the chocolate a diffraction grating. Now, to get the diffraction grating into a sugar candy, what we need to do is we need to create candy. And effectively what we're going to do is we're going to create a sugar glass. Glass is not just silica dioxide, which is what makes up the windows in this room. Glass is sort of a state of a material. And that state is essentially a supercooled liquid. Effectively, you've cooled it enough that the viscosity has risen to astronomical levels. And so for all intents and purposes, it appears to be a solid. But structurally, it is still an amorphous, chaotic mix of molecules. It's not crystalline. So in order to get very fine reproduction of profile in the surface, what we need to do is we need to prevent the sugar, as it cools, from crystallizing, because we'll tend to get a much smoother, glassier surface than the sort of rough, granular type of surface we would get from the crystallization. If anybody's seen rock candy, you know what I'm talking about. It doesn't tend to be shiny and clear and smooth. Now, to create a glass rather than a crystallization when the sugar cools, what we need to do is we need to introduce a contaminant or a doping to the sugar so that we inhibit the crystallization. And so when you make candy, you will always add a different sugar or a different material that will prevent the efficient packing or crystallization. Now, sucrose, which is table sugar, is a binary sugar. It's made up of two smaller sugar molecules and has a larger dimension than glucose, which is a single sugar. And by mixing in the glucose to the sucrose, we can create a good sugar candy. And because glucose is a little harder to obtain, you can do the same by getting corn syrup, which is essentially cornstarch in water. Cornstarch is made up of a long series of glucose molecules, and when you heat it up as you're making the candy, the starch decomposes into the individual glucose molecules, and so will create that mixture that prevents crystallization. Now, there's a lot of formulas for making hard candy, but the one that I found works here and is very easy to remember is you use 2 parts of sugar, 1 part of the corn syrup, and 1 part water. Now, the sugar, that's easy. You just put it in your pan, and the water is kind of interesting because it doesn't matter how much you use. You want to use enough so that when you heat up the sugar, it doesn't burn before it starts to dissolve into the liquid. But it doesn't matter if you use a lot of water, because effectively, as we heat it, the process of heating it and making the sugar candy is removing the water. And so when we reach the desirable temperature, which is called hard crack in cooking terms, but it means a final temperature of about 300 to 310 degrees Fahrenheit, we will have removed just the right amount of water, no matter what we started with. So I use 1 part water with 2 parts sugar simply because it's enough, but it doesn't make me sit at the stove for 2 hours. Now, the corn syrup is very viscous, and it's kind of hard to get it out of the cup. So a little trick that you can use is if you take the original container, pop the little metal seal that they have on the insides, or if you get it into a bin like this, you can place it in a microwave oven. And if you put it in for, say, a half a minute or so, bring it up to the temperature where it's just about uncomfortable to touch it. And what will happen is it will become much less viscous, and it'll pour out of the container much more easily. Once you've done that and you begin to heat up the sugar, it will begin to boil. And as it does, the water will be driven out, and you'll see a lot of bubbles forming on the surface. The process starts slowly because there's a lot of water. It takes a lot of heat to remove the water, and so the temperature will begin to rise very slowly. As you begin to approach the hard crack stage, which is 300 degrees, it accelerates very quickly. So initially you don't have to be very careful, but once you get to about 240, 250 degrees, you got to watch it very carefully so that you don't heat it too high. Above about 310 degrees, the sugar begins to decompose, and as a consequence, it begins to brown and caramelize, and that's not going to make a very good reflector. So now it's a little bit warmer. Probably could have done it a little bit longer, but you'll see the effect is that it makes the corn syrup a lot easier to get out of the container. Now once you stir this up and begin mixing it, you're going to probably be at the stove for about 10 minutes as you're bringing down the level of water in here. One thing I like to do is I actually use my thermometer as my stirrer. It's a little more convenient than using a candy thermometer, which always seems to tend to drop into the candy when it's least convenient to use. Now, the interesting thing about the film that we're going to use is you'll notice I have it mounted on this aluminum plate. And the aluminum plate is angled so that when I put the sugar on the top surface of the film, it will begin to run down over gravity and fill the grooves of the film. Note that you want to make sure that you've oriented the film properly so that the film is set up so that the grooves are running down with gravity. We don't want to produce a riffle table like we're panning for gold. And so you want to check to make sure that your film is profile side up. It's the side that has the most highest, brightest type of reflection from the room lights, and with the grooves running downward. And you can see that because if you look at room lights or you look at any kind of a light source, you'll see that the dispersion of the light is perpendicular to the direction that you want the sugar to run in. You'll also notice something else. Coming from the edge of this plate are a couple of wires to a variac. I use that because the variac allows me to warm up the plate to about 140 to about 180 degrees. And the reason for that is that the plate, if it's at room temperature, cools the sugar so quickly when it hits the film, it doesn't have the time to run into the grooves and fill them up. And you could do this without sort of a complicated setup like this. If you wanted to just take a marble plate or an aluminum plate, some sort of flat surface, put it in an oven for a while and bring it up to 160, 170 degrees right before you're ready to pour the sugar. This is kind of convenient because I can get the temperature up where I want it and just hold it there as long as I need it. But nevertheless, you'll also notice that there are a couple of bars that I have here. These are probably not necessary. I fabricated them when I thought it would be important because the film, when it comes in rolls, tends to bow out a little bit. As soon as you pour the sugar on this, it flattens out to the surface anyway, so you probably do not need these retaining bars that I have located here. The sugar itself, though, is going to take a little bit of time to dissolve. We're only at approximately the boiling point now, or not even there. So we may be at this for about 10 minutes to get it down to the hard crack stage. Now you see, as we get very close to the 300-degree mark, the syrup is becoming very thick and the temperature is rising pretty quickly. When we get to about 300 degrees, we're going to want to turn the heat down because the residual heat in the elements and everything will continue to carry it up higher than the 300. We don't want to overheat it. Now my plate temperature is just about right. And as I stir this and allow the cooler surface of the edges of the pan to cool off the liquid, the bubbles will simply shrink away and the liquid will begin to clear. It's usually a nice idea to continue stirring it so that you don't get this hard, gummy sugar on the edges of the pot and a clear mixture in the middle. It just makes it easier to handle. But you can see that the bubbles are rapidly disappearing. You're not going to be able to get rid of all the bubbles, but you can get rid of most of them, and they tend to rise away from the diffraction grating, so you won't see them in the surface that we're trying to profile. But you'll get a more transparent sugar and just a better appearance with fewer bubbles. Now the process of doing this part is to apply the sugar, or to put the sugar on the film near the top edge and allow gravity to carry it down the surface. And this is where warming the plate really makes a big difference. Now if you don't make a perfectly rectangular shape, you can obviously always trim this and cut this later. But I'm a bit of a neatness freak, so it's kind of nice to start out with something that's relatively close to the shape you're going to want to end up with. Now once the sugar has had a chance to spread over the surface, then it's a good idea to flatten it out so it doesn't continue to run over the edges. And so I'm going to pull out these little wedges and flatten this out. Another little trick is that in addition to the film on this surface, I also have a little sheet of polyester underneath it so it doesn't stick to the metal. So even though it's run over the edge of the film on the bottom, it's not going to cause a problem. Now at this point, what you can do is let it cool to room temperature, or you could put it in a refrigerator, or you could, because of our weather out here, run it outside of the garage for a few minutes, and in about 10 minutes it'll be about 10 or 15 degrees below Fahrenheit, below room temperature. And once it reaches that temperature, it's much easier to get it off of the film. And if you overcool it, like putting it in a freezer, it'll become so cold that when you bring it inside, water will condense on the surface, make it kind of cloudy, and can actually destroy the fine features of the grating. So you don't want to overcool it. So at this point, we're going to let this cool off. I'll show you the result in a sec. But we're going to begin the next part of the video with how you do chocolate. It's done substantially differently. Now the technique with working with chocolate is different because the material will not form a glass before it crystallizes. Essentially what happens is you have to lower the temperature below the point that you can work with it before it will form the glass transition. So we're actually going to have to work with a crystalline material, but what we want to do is work with the best, densest crystal form of chocolate that we can. And in cooking terms, it's called the beta crystallization of the cocoa butter, the triglyceride that makes up the bulk of the chocolate. There are about 5 or 6 different crystal forms, and if you can get the chocolate after you've melted it to sort of heart or cool and form primarily beta crystals. You're going to get the densest, highest melting point chocolate, and that's going to produce the best candy. It'll also produce the best profile when you try to mold the diffraction grating into it. When you buy chocolate, you buy it in the tempered form. And so what we're going to do is we're going to melt some of this chocolate. This is dark chocolate, and we're going to melt it in a double boiler to prevent it from burning. And we're going to bring this up to about 132, 134 degrees Fahrenheit. And as we do so, we're essentially breaking up all of the crystal forms and turning it into just a liquid triglyceride mixture of cocoa butter and some other products that make it dark chocolate. What we're going to do, though, when we temper it, is we are going to do a controlled crystallization. And effectively what that simply means is we're going to cool the chocolate by using tempered chocolate, which is in the beta phase, to act as sort of a skeleton or a guideline, so that as the chocolate molecules or the butterfat molecules begin to crystallize, they tend to crystallize in the form of that overwhelming form that's available in the cool chocolate, the stuff that you bought originally. So once we get this up to a boiling point, and we're going to use this probe again to measure this, we want to get it up to that temperature that I mentioned, which is about 130 degrees, 134 degrees. If you go too high, you'll obviously burn it, but you don't need to go any higher than that to cause the chocolate to become very liquidy and very useful. You want to be very careful about introducing any water. Water doesn't mix well with the oil and will form defects in the candy. So don't use wooden implements. Try to avoid getting any of the runoff from the double boiler in there, and you'll get a better mix. Now the temperature gauge on my little probe has a little trouble with the shallow layer of chocolate I'm using in here. But as I mix it around, you can see we're not nearly at that temperature yet. It doesn't take long, though. Make sure you get the edges, because you don't want to have any gummy, partially melted pieces of chocolate around the edges. They get harder to deal with later on. Now we're already at the right temperature, so I'm going to take this off the heat. And now we're going to begin the controlled crystallization. And effectively what we're going to do is break this up into as small a piece as you can manage, because that will help to get the surface area maximized and give the liquid chocolate more exposure to the framework that we're trying to recreate. There's a whole bunch of recipes you can find on Google or Wikipedia, candies, and different cooking shows. But effectively, no matter what ratios they talk about, what you want to make sure you have is that as you pass about 90 degrees Fahrenheit, as this cools, you want to make sure you still have some of that beta phase chocolate present to act as the guideline. This initial chocolate really is doing nothing other than just trying to bring the temperature down toward that point. The key is to make sure that there are some pieces of the beta phase chocolate or the tempered chocolate present when we cross that 90-degree threshold. I'm going to continue to add little pieces because I always want to make sure there's some, and it also speeds up the cooling process. Don't want to go too fast, because if you do, you will find that you'll get some unmelted chocolate present even when you get down to the desirable temperature of about 84 degrees. At that point, you've gotten the crystallization complete. And then what you can do is you can warm it slightly. Don't go above 90, but you can get it a little bit less viscous, and it'll make it easier to deal with. But you can see on the temperature gauge that the temperature is dropping pretty quickly. This doesn't take very long. And the smaller you make the pieces of chocolate, the better. Break it up. And make sure, again, you get the edges, because the glass is cooling off pretty quickly, and you want to make sure you get a pretty even distribution of temperature in there. Mixing with the probe like this is a real advantage, because you don't have to constantly re-measure the temperature. Now, as you can see, we're getting down at the lower 90s, and I still have a few particles of chocolate, so this is probably enough of the cooled tempered chocolate to this batch right here. Now I've gotten it close to the right temperature here. You can probably go a little bit cooler, but I think we're probably good enough. Now what I'm going to do is I'm going to place it back on the heat, and I'm going to raise the temperature just a few degrees. I don't want to exceed 90, but I want to make it as thin as I can. And so I'm going to try to warm this slowly a few degrees, and then we're going to take it off the heat. And rather than pour the chocolate across the film, because it's pretty viscous, I'm actually going to dip the chocolate film, the film, into the chocolate. And that will allow me to coat the film. And because I can dip it multiple times and it stays warm within the chocolate, what happens is the air bubbles that might form in those little grooves have a chance to kind of work their way out. And so if you'll notice on the plate next to me, there are two pieces of film that I've already pre-cut. And the reason for doing that is so that they would be a size that would fit this beaker. You could use bigger pieces if you had a bigger container. But I've oriented them such that they are lines up and profile up. And then I took a forceps, put a little marker tape on it so I'd know what I was doing once I coat the entire piece with the chocolate. Grab it, and this side represents the side we want up. Then I literally force the plastic into the chocolate. I'll draw it out a couple of times, and what I'm effectively doing is just rinsing, kind of causing a little bit of flow over the surface to get the bubbles to work their way up and out away from the plastic. And after I've done that about 3 times, then I'll take the chocolate out and I will place them on the cold metal that has a little polyester film on it, as you can see, that protects it so it doesn't stick to the aluminum. I'll do the second piece over here, again dipping it into the chocolate, profile side marked by the tape. And this works much better than trying to flow the chocolate over onto the cool plastic because it becomes just too viscous to work with. And then I'll place this next to it. Now you can see I have a few little bumps of chocolate on the upper surface. Don't worry about those, they'll disappear, or they're effectively on the surface that you don't care about. Now we're going to repeat this. We'll put this in the refrigerator, put this out in the garage, let it cool for about 20 minutes or so, and then we will demold them and see what kind of result we got. See you in a bit. All right. Let's see what we did. Now we'll start out with the sugar, this piece of film here, and basically you can just pull it away. The gloves are pretty important because it doesn't stick to your hands then, and you don't get fingerprints or oil on it. I'll pull this away from the surface, and I don't know if you can see it. Pretty good though, huh? Kind of neat. Now obviously it's a weird shape, but you can easily trim that with a razor blade. It's best to do it when you warm it up slightly so that it doesn't crack. Now the chocolate, always keep the surface that's important up. Chocolate can be a little more delicate to try to remove, but because there's chocolate on both sides, sometimes it's nice to take a little forceps or little probe to try to crack it away. You want to cause the break in the surface so you don't break the chocolate, and pull the bottom surface away from it. Try not to touch it again once you've done that because the surface is remarkably delicate. Pretty neat, huh? Now obviously to do such a good job takes a lot of practice. And the nice thing about this is that there's no chemicals, there's no products on here of any kind. I did try some spray lacquer, which is used for glazes. It's made out of essentially the exoskeleton from the lac beetle, and people can spray that on top of chocolate in order to give it a greater sheen. And it does add a little bit of a bitterness to the flavor, but what it also does is it sticks to the plastic better than the chocolate. So once you do that, you don't get the grating on the chocolate. You end up just ruining the result. So I wouldn't recommend using it. But as I said, this requires a lot of experimentation. I mean, if you screw up, it's usually a nice thing to know that you've got plenty of chocolate to work with. So I always recommend ordering this by the kilo, because you probably will find that even if you do a good job and you like the result, practice makes perfect.